So there's a couple of other equations you need to know about for simple harmonic motion, because there's more to simple harmonic motion than just pendulums. But we'll start off with a pendulum idea just to make sure you're aware of the pendulum equation. So obviously I alluded to the fact that the time period is the time taken to get from back there back. Well, say you can't measure a pendulum time period. Say you just want to know what the time period is. What are you going to do? Well, we need to know an equation for the time period. And the time period equation for a pendulum is 2 pi L over G. Now, how might we utilize this equation? And then generally it's done experimentally, but L is the length of the pendulum, the length of the string to the center of mass. And G is exactly what you think it is. It's G 9.81. The constant. So we've got the constant for the surface of Earth. So obviously G could change if you go to a different planet or you go somewhere else on the Earth. So this could change the value, but for the all intents and purposes, this works. Now, how is this equation often used? Well, this equation actually is often used to find G, because we can measure the length and we can measure the time period of a pendulum quite easily and get G. So how would we do it? Well, we have a graph, and we want to rearrange it so that the gradient equals G. Because if we have lots of different lengths and lots of different time periods, we'll want to put these on the axis so that the gradient will give G. So we can do some rearrangement of this equation to make that happen. So if we square both sides, we end up with t squared equals 4 pi squared L over G, because we square everything else. Then we can say that if we want the gradient to be G, we want to go 4 pi squared L over t squared will equal G. So that tells us what our axes are going to be. So we want t squared on the bottom here and 4 pi squared L, where L is the length of the pendulum that you're using. So you can use that to find G. And often is used to find G in various situations. And one of the better ways of finding G, if you're asking my opinion. So let's look at the other equation you need to know about. Well, there's not just pendulums that follow simple harmonic motion, but springs. So springs with a mass on the end, okay, can be displaced and then will undergo simple harmonic motion up and down to a amplitude, equilibrium, and amplitude, very same as the pendulum over here. But there's another equation for the time period of this, and bear in mind that all the equations we've done so far for simple harmonic motion are perfectly fine for springs and pendulums. They both do the same thing, they're both related to circular motion, so all those equations are good to go. So the equation for this one is that the time period is equal to 2 pi m over k. Well, very similar in nature. M is the mass of the pendulum, okay, as we'd expect here, and K is come back to haunt us from another set of videos, which is the force constant, or some might call the spring constant, for this spring arrangement. So again, we can use this situation to find T if we know M and K, but what if we want to find K? Well, we can do exactly the same thing as before. We draw a graph, we want the gradient to be K. We can use the same algebra as before. T squared equals 4 pi squared M over K. Therefore, 4 pi squared M over T squared will equal K. So that's our axes for our graph. And we can use that to work out the spring constant for any spring setup, or material for that matter. So that's just a brief introduction to these equations. I had no intention of deriving them. You can do that for your university thesis should you wish, but I'm not going to do it here, mostly because I don't know how to derive them. But for all intents and purposes, we've got two equations that you're going to need to use, and this is a common use for them and a common rearrangement for how they might be used.